So I want you to picture this. It is the spring of 1498.
Hmm.
The sun is just beating down on the wooden deck of a Portuguese caravel, and Vasco da Gama is standing there, staring out at the, well, to him, completely unfamiliar and treacherous waters of the Arabian Sea.
Right. He's totally out of his element.
Exactly. And, in the traditional Western history books that we all grew up reading, this is framed as this glorious dawn of the European age of discovery, right? Like, da Gama is about to reach India, open up the spice trade, and just permanently reshape global economics.
Yeah, it's a very triumphant narrative.
It is. But there is this really crucial detail missing from that story. Da Gama was completely out of his depth. I mean, he didn't know the monsoon patterns, he didn't know where the shoals were, and he was basically risking his entire fleet. The guy who actually took the wheel, the pilot who safely navigated that European fleet across the Indian Ocean, was a Muslim master navigator, a guy named Ibn Majid.
Yeah, and what's truly fascinating about that specific encounter is the technological disparity between them.
No, totally.
Because historical accounts suggest that when the Portuguese were eagerly showing off their navigational instruments, the tools they thought were absolutely cutting-edge, Ibn Majid wasn't amazed at all.
Not even a little bit.
No, he was actually completely unimpressed. Because the Muslim sailors navigating the Indian Ocean at that time, they already possessed superior devices. I mean, they had far more accurate maps. And this centuries-old tradition of deep maritime science that the Europeans were, well, they were just beginning to fathom it.
And see, that one moment right there, it totally shatters the ingrained expectation of the historical timeline we're all taught.
Oh, absolutely.
Because we learn history as this rickety bridge.
Yeah.
On one side, you have the Greeks and the Romans doing all this great philosophy and math, and then Rome falls, and humanity just kind of steps onto this dark, crumbling bridge that we literally call the Dark Ages.
Right.
And we're told everyone in Europe was just huddled around fires, struggling to survive, while all classical knowledge was locked away in these isolated monasteries. And then you don't get off that bridge until the European Renaissance. Boom, the lights come back on. Science is reborn.
It's a very neat, very comforting, and completely inaccurate narrative. Or, I mean, to be charitable, it's just missing the most dynamic part of the global picture.
Yeah.
Because if you step off that Eurocentric timeline, you realize that while Western Europe was, experiencing this period of intellectual contraction, an unprecedented intellectual explosion was actually happening in the Muslim world.
Which is exactly what we are exploring in today's deep dive. We are working our way through this massive, incredibly fascinating stack of historical texts today, specifically drawn from excerpts of A History of Muslim Philosophy.
Just a huge collection.
It really is. And we're looking at a millennium, a solid 1,000 years of groundbreaking advancements. We're talking geography, mathematics, astronomy, physics, chemistry. But our mission today isn't just to rattle off a list of inventions for you.
Right, that would just be a textbook.
Exactly. We want to understand how they did this, and more importantly, why. What were the cultural, spiritual, and highly practical engines that were driving this scientific golden age?
Because science never just happens in a vacuum. It's always driven by a need.
Right.
A society doesn't just wake up one Tuesday and decide, hey, let's invent algebra today, or let's build massive astronomical observatories. There are always underlying pressures, whether they're economic, religious, political, that force a culture to look closer at the mechanics of the world.
And for you listening, I want to stress that this isn't just dusty ancient history. Whether you are checking the date on your smartphone today, or relying on GPS to navigate a new city, or literally just using the number 0 to balance your budget, you are directly interacting with the legacy of the thinkers we're about to unpack.
It's woven into everyday life.
It really is.
Yeah.
So to figure out how this massive scientific boom started, we need to look at the literal ground under their feet, the foundation of it all. We have to start with geography.
Yeah, and the contrast in attitudes toward geography at this specific time in history is incredibly stark. Because our sources highlight that in the early medieval Christian world, scientific research into the physical earth was often viewed with, deep suspicion.
Right, because the focus was so different.
Exactly. The early church's focus was intensely spiritual and otherworldly. The prevailing thought was basically, if studying the physical world doesn't directly serve the salvation of your soul, then it's a frivolous distraction.
Or even worse, right? It was viewed as some kind of magic art.
Yeah, something pernicious and dangerous.
And there's this one historical figure mentioned in our sources who perfectly embodies this mindset. He was this 6th century sailor who became a monk, a guy named Cosmas Indicopleistes.
Oh, yes.
He wrote this deeply influential treatise called The Christian Topography, and his entire thesis, like the whole point of the book, was dedicated to disproving the ancient pagan idea that the Earth was a globe.
Which is just a tragic regression, really. I mean, the ancient Greeks had already proven the Earth was a sphere centuries earlier.
Right, Eratosthenes had even calculated the circumference with decent accuracy.
Exactly. But Cosmas rejected all of that empirical observation. He relied on this highly literal, very rigid interpretation of Scripture. Specifically, the descriptions of the tabernacle in the Old Testament to deduce the physical shape of the world.
Yeah, and he argued that the Earth was a flat, oblong rectangle.
Oh, rectangle.
Literal rectangle.
Right.
Because his logic was that it was twice as long from east to west as it was from north to south, just like the table of showbread in the tabernacle.
Right.
And to explain day and night, since he didn't believe in a globe, he claimed there was this massive conical mountain in the far north.
Mm.
And the sun, which he believed was pushed around by angels, by the way, just played hide and seek behind this mountain every evening.
It's wild. Our sources quote a modern historian who literally refers to Cosmas's work as systematic nonsense.
Systematic nonsense. I love that phrase.
It fits perfectly. Now, contrast that rigid anti-empirical stance with the early Islamic attitude that's described in our texts, because it was this atmosphere of enlightened curiosity.
Night and day difference.
Absolutely. And this wasn't just happenstance, you know. It was driven by both strict religious mandates and massive practical imperial needs. When the Islamic Empire rapidly expanded in the 7th and 8th centuries, stretching from the Iberian Peninsula all the way over to the borders of India and Central Asia, they absorbed this vast tapestry of cultures.
Right.
But they didn't just conquer territories, they aggressively assimilated knowledge.
And I want to dig into those religious mandates you just mentioned, because the Quran itself actually demands this kind of earthly observation, doesn't it?
It does.
Like it's filled with navigational terminology, talking about ships cutting through the sea and using the stars for guidance. But the real engine, the main catalyst of this geographic explosion, it has to be the Hajj.
Oh, without a doubt. The Hajj is the mandatory pilgrimage to Mecca that every able-bodied Muslim with the financial means must undertake at least once in their lifetime. So just think about the logistical reality of that mandate once the empire reached its zenith. You had this incredibly diverse population living in vastly different environments.
Yeah, you've got people up in the snowy mountains of Central Asia, people down in the blazing deserts of North Africa, merchants out on the humid coast of the Indian Ocean, and they are all legally and spiritually obligated to converge on one specific city in the Arabian Peninsula at a specific time of year.
It created the most intense, continuous international exchange of geographic data the world had ever seen. Every single year, this massive stream of travelers was traversing thousands of miles.
You couldn't just wander out of your house in Damascus or Cordoba and hope to stumble upon Mecca.
No, survival depended on hyper-accurate geographic knowledge.
You needed to know exactly where the wells were.
Yes.
You needed to know the topography, like which mountain passes were snowed in during which months, where the hostile territories were, where you could buy provisions along the way. It was basically this massive crowdsourcing of geographic data.
That's a great way to put it. And parallel to that spiritual mandate was the sheer bureaucratic nightmare of statecraft.
Oh, running an empire.
Right. The caliphs were ruling a continent-spanning empire. How do you govern if you don't know what you're governing? Our sources note that early Muslim geography actually evolved directly from what they called route books.
Route books?
Yeah, these were incredibly detailed administrative manuals, books of roads and kingdoms, they called them, designed initially for the Imperial Postal Service and for the tax collectors.
Well, yeah, because you can't tax a farm if you don't know exactly where it is, what kind of soil it has, and what crops it yields.
Precisely. So the early geographers were highly practically motivated. They were taking the foundational texts of the ancient Greeks, particularly Ptolemy, and using them as a starting point.
Right, but they weren't just passively translating and copying Ptolemy like it was Holy Scripture.
No, not at all. They were out there walking the earth, and they were fact-checking the ancients through lived, grueling experience.
I love this part of the history because Ptolemy's method for mapping the world was deeply mathematical, but it was incredibly detached from the human experience on the ground. Like the Greeks divided the known world into these hypothetical horizontal latitudinal strips called climatic zones.
Yeah, it was a very rigid geometric way of slicing up the planet based purely on latitude and the length of the longest day of the year in that specific strip.
See, it makes me think of trying to understand a massive, culturally rich city by only looking at a zip code map.
Oh, that's a good analogy.
Right. Like a zip code is a useful administrative boundary for the post office, but if you look at a zip code on a piece of paper, it tells you absolutely nothing about the architecture or the food, the spoken dialects, or the actual lived environment inside that little line. It's this artificial grid placed over a living ecosystem.
That is a perfect analogy for why the Muslim geographers ultimately discarded the Greek climatic system. The texts highlight this Arab geographer named al-Istakri in the 10th century, who essentially realized the system was useless for truly understanding a place.
Because the climate varies so much.
Exactly. The climate in a single latitudinal strip can vary wildly depending on altitude, ocean currents, and prevailing winds. You can't just draw a straight horizontal line and say, everything here is the same. So al-Istakri and his contemporaries pivoted. They pioneered what modern academics now call regional geography.
Meaning they stopped looking at math lines and started looking at the actual landscape.
Right. They began to divide the Islamic world into natural geographic regions. They studied the physical environment, the topography, the local flora and fauna. And crucially, they connected that to the human element, the people, their cultures, and their economic activities.
They were essentially doing human geography and sociology like a millennium before those became formal academic disciplines in the West.
They absolutely were. There was another brilliant figure mentioned, al-Madisi, who spent decades traveling specifically to write a comprehensive geography based solely on direct observation. He wanted to understand the causal relationship between a physical environment and the character of the people living there.
And when we talk about travel in this era, the scale of it is just mind-boggling. In Western education, Marco Polo is always held up as the gold standard of medieval travel, right? Like he went to China, came back, wrote a book. He's the legend. But our sources introduce us to Ibn Battuta.
Oh man, if Marco Polo is a marathon runner, Ibn Battuta is an ultra-endurance athlete.
Seriously.
Ibn Battuta left his hometown of Tangier, Morocco in 1325, ostensibly just to make the Hajj to Mecca. He was a 22-year-old scholar of Islamic law, but he just kept going.
He didn't come home for 30 years. I mean, what kind of mileage are we actually talking about here?
Historians estimate he traveled roughly 75,000 miles.
75,000 miles. That is 3 times the circumference of the Earth.
Yeah.
On foot, on the backs of camels, in little wooden sailing dhows.
He traveled across North Africa, through the Middle East, down the Swahili coast of East Africa, over to India, where he actually served as a judge for the Sultan of Delhi for a while, down to the Maldives, through Southeast Asia, all the way to China, and then finally back to Spain and Morocco.
It's unbelievable.
He survived shipwrecks, he survived pirate attacks, and the bubonic plague. And what is most astounding is that his famous travelogue, the Rila, wasn't written from some stack of meticulous journals he carried around. He dictated the vast majority of it entirely from his phenomenal memory when he finally returned to the court in Fez.
The sheer volume of descriptive data that guy held in his head is staggering. But here's the natural problem. You can only describe a 75,000-mile journey in words for so long, right?
Right.
Eventually, a massive empire needs to visually represent that data. Words can describe a trade route, but if you're a captain steering a ship loaded with, insanely valuable spices across the open ocean, poetry and travelogues aren't going to keep you off the reefs. You need charts. You need absolute precision.
Which marks the crucial transition from textual geography to advanced cartography and maritime navigation. The need for precision wasn't just some academic luxury, it was a matter of life, death, and immense economic consequence. And this is the arena where the reverence for ancient Greek knowledge hits a wall of hard, empirical reality.
This is where Ptolemy gets rigorously audited. Because our sources show that Ptolemy, despite his absolute genius, made some terrifyingly large errors in his calculations.
He really did. Ptolemy severely underestimated the overall size of the Earth, and he drastically exaggerated the length of the Mediterranean Sea. He estimated the Mediterranean to be about 62 degrees of longitude from the Strait of Gibraltar all the way to the coast of the Levant.
And what is the actual measurement?
It is roughly 42 degrees.
That is a 20-degree margin of error.
Yeah.
In navigational terms, a 20-degree error is catastrophic. If a captain is sailing by dead reckoning or early celestial navigation based on a map that is 20 degrees off, they're going to smash into a coastline days before they expect to. Or they're going to run out of fresh water and starve in the open ocean because the journey is drastically longer than the map indicated.
Exactly. But the wild thing is, our sources point out that European mapmakers held on to Ptolemy's 62-degree mistake all the way up until the 16th century. They treated his texts like unassailable dogma.
Meanwhile, Muslim cartographers had corrected that 20-degree error centuries earlier.
They had to. The Mediterranean was a bustling, contested highway for them, but their maritime expertise extended way beyond just that inland sea. They were mastering the treacherous currents of the Red Sea, the tidal extremes of the Persian Gulf, the vast expanse of the Indian Ocean, and the island labyrinths of Southeast Asia.
And the maps they produced to organize all this knowledge weren't just functional. They were stunning pieces of high art and diplomacy. Our texts highlight al-Idrisi in the 12th century, and his story is just a beautiful example of cross-cultural collaboration in an era we often assume was just endless religious war.
Al-Idrisi is a remarkable figure. He was born in Islamic Spain, educated in Cordoba, and traveled extensively. But he eventually settled in Palermo, Sicily, at the court of King Roger II.
A Christian king.
Right, a Christian Norman king who was deeply fascinated by Islamic science and culture.
Roger basically gave him unlimited funding to create the ultimate map of the world.
Yes. Al-Idrisi spent 15 years compiling data from ancient texts, contemporary Arab geographic manuals, and personally interviewing travelers passing through Sicily. And the final product wasn't just some parchment scroll. He created a massive, solid silver planisphere, a world map engraved onto a gigantic silver plate.
Oh, wow.
Yeah, and it was accompanied by a massive book called the Book of Roger, which is arguably the most elaborate, accurate description of the world produced in medieval times. He essentially synthesized the corrected Greek math with the empirical data of Arab merchants.
But obviously, working sailors weren't carrying giant silver plates onto their ships. The sources talk about the working charts, right? The tools of the trade.
Right. For the actual mariners, the Arabs developed incredibly detailed sailing instructions and coastal charts, which the Europeans later adopted and called portolani. These weren't maps in the modern sense. They were networks of rum lines crisscrossing the sea, showing the exact compass bearings between major ports.
And the men who created and read these charts were highly revered. The texts call these expert pilots the Lions of the Sea.
They definitely earned that title. Navigating the Indian Ocean is profoundly different from navigating the Mediterranean.
Because of the winds.
Exactly. It's governed by the monsoon winds, which reverse direction completely twice a year. If you don't understand the complex meteorology of the monsoons, you will die at sea. These lions of the sea had an intricate understanding of wind patterns, hidden reefs, and celestial navigation.
Which brings us perfectly back to our hook, to Ibn Majid, the Lion of the Sea, who saved Vasco da Gama. Because when you realize the depth of this cartographic tradition, that encounter in 1498 makes total sense.
Completely.
Da Gama wasn't sailing into some unknown void. He was stumbling into a highly sophisticated, meticulously mapped, centuries-old maritime highway. The European age of discovery was essentially heavily subsidized by Islamic cartography.
It really forces us to reevaluate the way we frame historical narratives, doesn't it? But there's a deeper layer to this, because you cannot correct the length of the Mediterranean by 20 degrees, and you certainly cannot calculate a rum line across the open Indian Ocean using just guesswork. Cartography at this level is fundamentally an exercise in high-level math.
Exactly. You hit a mathematical wall. You can't project a three-dimensional globe onto a two-dimensional map or calculate celestial angles without a serious upgrade to the mathematical toolkit, which takes us into the realm of pure numbers. Math and algebra.
Yes.
Now, I know the word algebra might trigger cold sweats for anyone who struggled in high school math.
Me included.
Right. But the story of how this language developed is thrilling, because it starts with a massive structural problem, the way the Western world actually wrote numbers.
Up until this period, much of Christian Europe and the remnants of the Roman world were still heavily relying on Roman numerals. Now, Roman numerals are fine for, carving a date into a stone monument or counting small inventory. But imagine trying to do long division or calculate the trajectory of a star using Roman numerals.
It's a nightmare. Try multiplying 4 teeth by XL8. You spend half your time just trying to decipher the letters before you even do the math.
It is entirely unsuited for complex theoretical math. The Arabs, however, recognized a superior system further east. They adopted and systematically refined the Hindu numerical system, what we now call Hindu-Arabic numerals, 1, 2, 3, 4, 5, 6, 7, 8, 9.
But those 9 digits aren't enough. The absolute game changer, the intellectual leap that alters human history, was the formal integration of the concept of zero.
Yes. Introduced and formalized for the Islamic world by the Persian polymath Al-Khwarizmi in the 9th century.
Let's really break down why zero is so important. Because to a modern person, 0 is obvious. It just means nothing. You have 0 apples. But philosophically, in ancient times, the concept of a number representing nothing was actually quite terrifying to some cultures.
The Greeks hated the idea of a void.
Right. But without 0, you cannot have a place value system.
Exactly. Place value is the idea that the position of a digit changes its value. A 5 foot can mean 5, 50, or 500. Without a symbol for 0 to act as a placeholder, how do you easily distinguish between the number 15, the number 105, and the number 1500?
In older systems, it was often based on context, which is disastrous for precision.
0 anchors the entire system. It allows numbers to scale infinitely in either direction, up to millions or down to microscopic decimals.
Without 0, the binary code that runs the digital recording of this very deep dive wouldn't exist.
Al-Khwarizmi's systematization of these numerals fundamentally reorganized human thought. In fact, his influence is so pervasive that the word algorithm, the logic sequences that run our social media feeds, our banking, our internet searches, is just the Latinized corruption of his name. Al-Khwarizmi was translated to algorithmy, which became algorithm.
So the grandfather of computer science lived in a 9th century Baghdad library.
Basically, yeah.
But his legacy goes even further, because he didn't just give us the tools to write numbers, he gave us a new way to manipulate them. He is universally recognized as the father of algebra. The word comes directly from the title of his most famous book, Al-Jabr.
And what Al-Khwarizmi accomplished with algebra was a profound philosophical shift. The ancient Greeks, like Euclid, were brilliant geometricians, but they thought of math almost entirely in terms of physical magnitudes. The length of a line, the area of a square.
You had to be able to draw it.
Yes. Al-Khwarizmi abstracted it. He conceived of numbers not as physical shapes, but as relations. Al-Jabr literally refers to the operation of restoring or balancing an equation. He formalized the process of solving for an unknown variable, what we call x.
Right.
He created a system where you could manipulate symbols on both sides of an equation until the unknown became known. He liberated mathematics from the constraints of pure geometry.
He gave us a universal language. But the texts show that this math didn't stop evolving with him. A few centuries later, another mathematical heavyweight enters the scene, a name many listeners might recognize, but probably for a totally different reason, Umar al-Khayyam.
Yeah, in the Western literary canon, Umar Khayyam is famous almost exclusively as a poet. He is the author of the Rubaiyat, a jug of wine, a loaf of bread, and the Awham, the romantic, philosophical poet.
I remember reading his poetry in college. It's beautiful, very fatalistic stuff, but our sources make it abundantly clear that poetry was essentially his side hustle.
Exactly.
His real claim to historical immortality is his mathematics.
He was a mathematician centuries ahead of his time. Khayyam tackled problems that were immensely complex, specifically dealing systematically with cubic equations.
Okay, let's pause and explain what that meant for a scholar in the 11th century, because they didn't have the modern algebraic notation we use today. When we say a cubic equation, we mean an equation where the variable is cubed, like x to the power of 3. How did he solve those without modern graphing calculators?
He used a brilliant synthesis of algebra and geometry. Khayyam realized that you could find the roots of a cubic equation by drawing intersecting conic sections.
Conic sections meaning shapes sliced out of a cone, like circles, parabolas, and hyperbolas.
Exactly. If he had a complex cubic equation, he would geometrically draw a specific parabola based on the equation's parameters, and then draw a specific circle that intersected that parabola. The physical distance from the point where those two shapes crossed down to the horizontal axis gave him the mathematical solution to the equation.
So he was visually graphing algebraic solutions hundreds of years before Descartes invented the Cartesian coordinate system.
He was.
It's stunning. But let me push back here for a second. Or rather, let me ask the question you're probably inevitably thinking right now.
Yeah.
It is undeniably brilliant to intersect parabolas on a piece of parchment. But was this just elite intellectuals flexing on each other? Did solving a cubic equation actually have a tangible impact on daily life in the 11th century?
That is the essential question. Theoretical math is beautiful, but applied math changes the world. And the answer is yes, it had massive, immediate practical application. The best example in our sources revolves around timekeeping.
Oh, the calendar.
Right. In the late 11th century, the Seljuk Sultan, Malik Shah, realized he had an administrative crisis on his hands. The existing calendars were slipping heavily out of sync with the actual solar year.
Which is a disaster if you run an agrarian empire. If your calendar says it's time to plant the wheat, but the solar year says it's still freezing, your empire starves. You need to know exactly when the vernal equinox is.
Precisely. You need absolute alignment between the civil calendar and the cosmos. So the Sultan tasked Umar Khayyam and a team of astronomers at the observatory in the city of Ray to fix time itself.
Wow.
Khayyam used his incredibly advanced mathematics and astronomical observations to create the Tariq al-Jalali, the Jalali calendar, which was instituted in 1079 AD.
And how did he solve the drift? Because a solar year isn't exactly 365 days, it's roughly 365 and a quarter days, which is why we have leap years.
To keep the calendar perfectly aligned with the sun, Khayyam introduced a highly complex, mathematically elegant system of intercalation adding leap days. Through meticulous calculation, he figured out that the most accurate cycle required adding 8 intercalary days every 33 years.
Okay, let's look at the result of that math. How accurate is Khayyam's calendar compared to the one we use today?
The math is stunning. Khayyam's formula results in a calendar that has an error of exactly 1 day every 5,000 years.
1 day of drift every 5 millennia.
Now compare that to the Gregorian calendar. That is the standard calendar the entire world operates on right now, established by Pope Gregory III in 1582, 500 years after Khayyam. The Gregorian calendar has an error of 1 day every 3,330 years.
I want to make sure you really absorb that. The digital calendar programmed into your smartphone right now, the calendar that coordinates global financial markets and international flights today, is mathematically less accurate than the one a Persian poet invented nearly 1,000 years ago using intersecting parabolas.
It perfectly illustrates how high-level theoretical mathematics directly translated into the mastery of the physical world. And here is the logical progression. Once you have advanced geometry, a solid grasp of algebra, and the precision of the number 0, your ambition naturally scales up. You are no longer limited to measuring the boundaries of an empire or organizing the days of the year.
You can measure the heavens.
Exactly. The mathematics demanded astronomy.
And this shift into the golden age of astronomy is where the scale of the science becomes truly colossal. You know, when I used to think of medieval astronomy, I pictured a lone, bearded genius freezing on a rooftop, squinting through a brass tube.
Right, the lone scholar.
Yeah. But our sources describe something entirely different. They describe the birth of what we would call big science.
That is the perfect term for it. Prior to this, astronomy was largely an individual pursuit or funded haphazardly by wealthy patrons. But in the Islamic world, you see the institutionalization of science. The creation of massive, state-funded observatories.
State-funded?
Yes, we are talking about institutions funded by the imperial treasury, employing vast collaborative teams of specialized scientists, mathematicians, theoretical astronomers, and highly skilled instrument makers.
These observatories in places like Baghdad, Moraga, and Samarkand, they were basically the medieval equivalents of NASA's space centers, or the CERN particle accelerator in Switzerland today. They were massive government infrastructure projects dedicated purely to data collection and discovering the physical nature of the universe.
And the physical instruments they engineered for these observatories were staggering in their size and ambition. Because the fundamental rule of pre-telescopic astronomy is, the larger the instrument, the finer the degrees you can measure.
The sources detail the observatory built by Ulugh Beg in Samarkand in the 15th century. And Ulugh Beg wasn't just a royal patron paying for the building. He was the grandson of the conqueror Timur, the ruler of the empire, and a brilliant practicing astronomer in his own right.
To get the most accurate possible measurements of the stars' altitudes, Ulugh Beg's team constructed a meridian arc, a massive quadrant.
Can you explain how a quadrant works just so we can visualize it? What does it actually do?
Think of a protractor you used in grade school geometry, but scaled up to architectural proportions. A quadrant is a quarter of a circle, marked with degrees. By sighting a star along the curve of the quadrant, you can measure its exact angle above the horizon. A small handheld quadrant gives you a rough angle. But Ulugh Beg wanted absolute precision, so he built a quadrant so enormous that its arc was dug deep into the bedrock of a hill.
The texts. The diameter of this quadrant was equal to the height of the Hagia Sophia church in Istanbul.
It's massive.
They were building subterranean skyscrapers just to track the stars.
By making it that massive, the individual degree marks on the curved track were spaced far enough apart that they could subdivide them into minutes and seconds of a degree. It allowed them to produce star catalogs of unprecedented accuracy.
But even centuries before Ulugh, like back in the 9th century, they're doing massive collaborative science. The sources talk about the Caliph al-Ma'mun ordering a geodetic survey to measure the exact circumference of the Earth. And the way they did it is a masterclass in applied geometry.
It is brilliant. Al-Mamun dispatched 2 teams of scientists and surveyors out into the flat, blistering plains of Sinjar in the Syrian desert.
How do you measure the globe with ropes in a desert?
They used astrolabes' intricate, handheld brass analog computers that calculate the position of the stars. The teams first used an astrolabe to measure the exact altitude of Polaris, the North Star, from a specific starting point. Say it was at 34 degrees above the horizon. They drove a stake into the ground. Then the teams walked in a perfectly straight line due north, physically measuring the ground as they went.
Laying down wooden rods and pulling ropes, counting every single yard, baking in the sun?
Exactly. They walked straight north until they took another reading with the astrolabe and found that Polaris was now at exactly 35 degrees above the horizon.
Meaning they had traversed exactly 1 degree of the Earth's curvature.
Yes. They measured the physical distance of that 1 degree on the ground and then simply multiplied that distance by 360 to find the full circumference of the Earth.
And what was their final calculation?
They calculated the Earth's circumference to be roughly 20,400 Arab miles. When you convert the medieval Arab mile to modern measurements, their calculation comes out remarkably close to the actual figure of about 24,900 English miles.
That's crazy.
They calculated the size of the planet to within a tiny margin of error in the 9th century by walking in the desert with brass dials and ropes.
It's astounding. But for me, the absolute apex of this astronomical golden age, the most mind-bending leap of physics mentioned in our sources, comes from al-Biruni in the 11th century. Al-Biruni is one of those historical figures who makes you feel deeply unaccomplished.
Oh, absolutely.
He was a physicist, an astronomer, a linguist, and basically the world's first anthropologist. And in 1030 AD, he casually discusses the theory that the Earth is rotating on its axis.
Let's contextualize that date. 1030 AD. Copernicus doesn't publish his heliocentric theory until 1543. Galileo faces the Inquisition in 1633. Al-Biruni is tackling the mechanics of a moving Earth half a millennium earlier.
The Greek dogma, handed down from Aristotle and Ptolemy, was that the Earth was the heavy, stationary center of the universe. If the Earth was spinning, the Greeks argued, birds would be ripped from the sky, and if you dropped a rock, it would land miles away because the Earth would have moved beneath it. How did al-Biruni counter that?
Al-Biruni used a breathtaking physical argument that prefigures modern physics. He reasoned that if you drop an object from a height, it actually does not fall perfectly straight down in a perpendicular line. He theorized it inclines slightly to the east.
Wait, why?
Because, as he argued, the falling object possesses 2 motions simultaneously. It has the straight downward motion of falling toward the center of the Earth due to gravity, but it also retains the circular motion it had from the Earth rotating beneath it before it was dropped. Because the Earth is spinning eastward, the falling object is carried slightly eastward as it falls.
He is conceptualizing the conservation of momentum and the effects of a rotating reference frame.
Yes.
He is predicting the Coriolis effect hundreds of years before classical Newtonian mechanics existed. He didn't have a telescope. He just had a rigorous, fiercely critical mind that was willing to dismantle established dogma based on mathematical logic.
He was willing to ask the questions that disrupted the entire medieval worldview. And the legacy of al-Biruni and his peers isn't just locked in old manuscripts. It is quite literally written in the sky above us.
If you go out tonight, stand in your backyard, and look up at the stars, you are speaking Arabic.
The linguistic legacy is indelible. Almost the entire nomenclature of modern classical astronomy is Arabic.
Words we use all the time to map the sky. Zenith, which is the point directly above. Nadir, the point directly below. Azimuth. And the names of the most famous stars in the galaxy. Altair, Vega, Aldebaran, Rigel, Betelgeuse. These are all Arabic names, either given originally or preserved by these Muslim astronomers.
That's
Every single time a modern astronomer looks through a multi-billion-dollar telescope, they are operating within a framework built by these scientists.
But speaking of looking through telescopes, that brings up a profound physiological question. If you are building giant quadrants and dedicating your life to measuring starlight, you eventually have to ask, how are we actually seeing that light?
Right. What is the physical mechanism of sight? Which bridges us perfectly into the realm of physics, specifically optics, because understanding the stars requires understanding the nature of light itself.
For centuries, the undisputed authority on how human vision worked came from the ancient Greeks, primarily Euclid and Ptolemy. They championed what was called the emission theory.
The emission theory.
Right. They theorized that the human eye actively emitted invisible visual rays, almost like invisible tentacles or a flashlight beam, that shot out of the eye, bounced off external objects, and returned to the eye, carrying the visual information.
I mean, I guess it makes intuitive sense if you're walking in a dark forest at night. You feel like you were actively looking for something, straining your eyes to cast out and find the path. But logically, it falls apart instantly.
Completely.
If my eyes are shooting out visual rays, why can't I see in a pitch-black room? Or even crazier, when I open my eyes and look up at the night sky, did my eye rays just travel millions of light years across the universe in a fraction of a second to hit a star?
Exactly. The physics of it make no sense. And the scientist who finally recognized this and systematically shattered the Greek emission theory was Ibn al-Haytham, known in Western Europe as al-Haytham. He lived in the 10th and 11th centuries and is universally regarded by historians of science as the foremost physicist of the Middle Ages.
What did his experiments look like? How did he prove the Greeks wrong without modern lab equipment?
In his magnum opus, the Book of Optics, Ibn al-Haytham didn't just theorize, he relied on rigorous, repeatable experimentation. He mathematically and experimentally proved the intermission theory that light does not originate from the eye.
So it comes from outside.
Yes, light originates from luminous bodies like the sun, a fire, or a lamp, bounces off physical objects, and enters the eye. Vision is a passive reception of light rays, not an active emission.
And he proved this using the camera obscura, right? The darkroom experiment.
Yes, the camera obscura is the perfect demonstration of his genius. He would take a completely dark room or tent and make a tiny pinhole in one wall. Outside the room, he would set up multiple different lanterns at different heights and angles.
Okay, so you have a dark room, a pinhole, and glowing lanterns outside. What happens on the inside?
On the blank wall inside the room, opposite the pinhole, the light from the lanterns would project upside down. Crucially, Ibn al-Haytham showed that the light from each separate lantern traveled in perfectly straight lines, passed through the single pinhole, crossed over each other without mixing or blurring, and hit specific spots on the back wall. If he covered one lantern outside, its specific projection inside vanished.
It's the exact mechanical principle of a modern camera.
Exactly. And by mapping the geometry of those light beams, he proved that light travels in straight lines from the source independently of the human eye. He proved that the eye is just a biological camera. Obscure light enters through the pupil and projects onto the retina.
He also studied refraction, right? Like how light bends when it moves through different mediums, like air into water or air into glass. He studied the magnifying power of curved lenses. He even calculated the duration of twilight by measuring the refraction of sunlight in the atmosphere and used that math to estimate the physical height of the Earth's atmosphere.
His work is foundational.
But here is my big question. It's the paradox of this whole era. If Ibn al-Haytham completely mapped the mathematics of how light bends through a lens in the 11th century, why didn't the Islamic world invent the telescope? Why did humanity have to wait until the 17th century for Galileo and the Dutch spectacle makers? They had the math.
It is a brilliant question, and it highlights the harsh reality of scientific progress. There is a massive gulf between theoretical physics and applied material engineering.
Oh, the materials.
Right. Ibn al-Haytham understood the geometry of lenses perfectly. He could draw the diagrams of how a telescope should work. But to physically build one, you need more than diagrams. You need glass.
And not just any glass.
No, you need the industrial technology to manufacture incredibly pure, optically clear, flawless glass, and then the mechanical tools to grind that glass into microscopically precise convex and concave curves. The glass-making technology in the Islamic world at that time was fantastic for decorative arts, for beautiful vases and lamps, but it was not capable of producing the optical-grade purity required for a telescope. The physics was centuries ahead of the metallurgy and material science.
So you can write the software code perfectly, but if the microchip hasn't been invented yet, you can't run the program.
Precisely. But even without the hardware, their theoretical breakthroughs in physics kept coming. The sources highlight another physicist, Qutb Shirazi, in the 13th century. He was the first person in history to give a completely correct, mathematically rigorous explanation of the rainbow.
The rainbow. Something humans have stared at with mystical awe since the dawn of our species.
Shirazi demystified it. He mapped the exact pathway of light. He proved mathematically that the primary rainbow is caused by a ray of sunlight entering a microscopic spherical water drop in the atmosphere, refracting, bending as it enters, then reflecting off the inside back wall of the water drop, and refracting a second time as it exits the drop and travels to the observer's eye. 2 refractions and 1 internal reflection.
In Western textbooks, René Descartes almost always gets the credit for deciphering the rainbow. But Shirazi had the geometry locked down centuries earlier.
And we cannot forget Al-Biruni in this context either. While studying these optical phenomena, he made a conceptual leap that is foundational to modern physics. He realized and argued that the velocity of light is enormously greater than the velocity of sound.
Which is something we experience intuitively when we see a flash of lightning seconds before we hear the thunder. But to formalize that conceptually into a framework of physics, to declare that light is a physical energy with a finite speed, is a major paradigm shift.
It is.
Okay, I want to pull the camera back for a second and look at the trajectory we've been on. We started with the practical need to navigate deserts for the Hajj and map trade routes. That forced a mathematical revolution. Algebra 0, cubic equations. That math was scaled up to build massive observatories, track the stars, and calculate the rotation of the Earth. Tracking the stars led to decoding the physics of light, proving how our eyes work and how rainbows form.
It's all connected.
You have these brilliant minds realizing that the physical world, light, gravity, momentum, is governed by invisible, measurable laws and energies. They are measuring the specific gravity of matter. Al-Biruni accurately measured the density of 18 different precious stones and metals.
They are realizing that matter is not static, it is dynamic, and it follows rules.
And if you realize that matter follows rules, if you can measure its density and understand the energy of light, the ultimate scientific temptation arises. The next logical leap is asking, can we change the matter? If we understand the building blocks, can we manipulate them? Can we transmute one thing into another?
The alchemy question.
Which brings us to the final, and perhaps most misunderstood, branch of science in this era, the mystical science of chemistry and its predecessor, alchemy. Now, when most people today hear the word alchemy, they immediately picture a crazy bearded wizard in a dark, crumbling tower, boiling vats of lead, desperately trying to turn it into gold so he can get fabulously rich.
A total charlatan.
Exactly. We view it as a total scam, a pseudoscience born of greed. But our sources paint a much more complex, deeply philosophical, and frankly, deeply spiritual picture of what alchemy actually was in the Islamic world.
To understand Islamic alchemy, we have to trace its linguistic and cultural roots, which, surprisingly, point heavily toward China, not just Greece.
Wait, China?
Yeah. The English word alchemy comes directly from the Arabic alchimia, and etymologists believe kimia likely derives from an ancient South Chinese dialect term, kimia, which translates roughly to gold-making juice.
Gold-making juice. That instantly shifts the perspective. It implies a liquid, a potion, a transformative elixir, rather than just hitting a piece of lead with a wand.
Exactly. And speaking of the word elixir, that also comes directly from the Arabic elixir. But here is where the Western Harry Potter-esque concept of alchemy completely misses the mark. In the Muslim world, fabricating physical gold to buy a bigger palace was rarely the ultimate goal of the true masters of the craft.
Then what was it?
Alchemy was profoundly tied to mysticism, specifically to Sufism, the esoteric, mystical branch of Islam.
This is the part of the sources that blew my mind. They state that the primary goal of the alchemist was to find a panacea, a life-giving principle. It was about achieving simultaneous spiritual and physical salvation. So the obvious question is, how does turning a lump of cheap iron into gold equal spiritual salvation?
It requires us to understand their animistic view of the universe. The foundational theory of Islamic alchemy, heavily developed by the man known as the father of Arab chemistry, Jabir ibn Hayyan, was the sulfur-mercury theory of metals. But we must be careful here. When Jabir said sulfur and mercury, he didn't mean the yellow powder and the toxic liquid metal we find on a modern periodic table.
Right. They were using those words as metaphors for cosmic energy.
Yes. They believed that everything in the physical universe possessed a body and a soul. The body represented negative, passive, frozen energy, which they called the mercury principle. The soul represented positive, active, fiery energy, the sulfur principle.
Okay.
They believed that in base metals like lead, iron, or copper, The body and soul were fundamentally out of balance. The metal was essentially sick or corrupted by earthly impurities.
So under this philosophy, gold wasn't just valuable because it was shiny or rare. Gold was revered because it was the one perfect, incorruptible metal. It doesn't rust, it doesn't tarnish, it doesn't degrade. Gold was matter in a state of absolute cosmic perfection and balance.
Precisely. Therefore, the alchemical process, the endless cycles of heating, dissolving, calcining, and distilling, was a physical metaphor for the spiritual purification of the human soul. The alchemist was trying to violently separate the active soul of a substance from its corrupt body, purify both elements in the fire of the laboratory, and then reunite them in perfect divine harmony.
It makes me think of extracting the essential oils from a flower to make perfume. If you want to capture the absolute essence of a rose, you take a massive field of roses, you crush them, you boil them in water, you capture the steam, and you meticulously distill it down over and over again until you are left with one tiny vial of pure, intensely aromatic rose essence.
Yes.
You have violently discarded all the heavy, dead, decaying plant matter, and you have preserved only the immortal soul of the flower.
That analogy is perfect, because distillation was one of the primary techniques perfected by these alchemists. Jabir ibn Hayyan is credited with inventing or heavily refining the alembic still, the very apparatus used to distill liquids, which is still the foundational tool in chemistry in the modern spirits industry today.
Yeah.
They're desperately trying to extract the pure, uncorrupted essence of matter, the ixer, the elixir.
And the belief was that if you could successfully create this perfect pure elixir in the lab, you could apply a tiny drop of it to a sick base metal like lead, and it would instantly heal it, transmuting it into perfect gold.
And by extension, if a human being consumed the elixir, it would heal all biological imbalances, cure all diseases, and grant immense, perhaps eternal longevity. They weren't just trying to get rich, they were trying to hack the code of mortality. They were trying to cure the disease of decay itself.
It's an incredibly beautiful, ambitious philosophy. But what makes Jabir ibn Hayyan so important to the history of science is that while his underlying theory was highly mystical, his daily methods were rigorously empirical. He wasn't just sitting on a rug meditating about sulfur and mercury. He was in a laboratory covered in soot.
He was a highly disciplined experimentalist. Jabir insisted on exact measurements and controlled conditions. He classified chemicals based on their properties. He described the chemical processes of calcination, crystallization, sublimation, and evaporation. He figured out how to synthesize basic acids. He was doing hard, dangerous, hands-on chemistry.
And according to the historical record, he was highly successful at it. The sources shed this amazing archaeological anecdote about Jabir that feels like it belongs in an Indiana Jones movie.
It really does.
Jabir lived in the 8th century. About 200 years after his death, during a period of urban renewal, workers were demolishing some old houses in the city of Kufa, in Iraq, right in the neighborhood where Jabir was known to have lived and worked.
And in the rubble, they discovered a hidden subterranean laboratory.
Right, and inside this preserved lab, they found a mortar, the heavy bowl used by chemists for crushing and grinding raw minerals. But this mortar wasn't made of stone or ceramic or brass. The workers found a solid gold mortar weighing 2.5 pounds.
Which is a profound discovery because it proves two crucial things about Jabir. First, it proves that he was a highly successful, practical chemist who had accumulated immense physical wealth through his metallurgical skills. But more importantly, it proves the deeply ascetic, Sufi nature of his life. He had a 2.5-pound block of solid gold, a king's ransom, and he didn't use it to buy a palace or fund a private army. He molded it into a bowl to grind sulfur and salt. He used it as a utilitarian tool for his art. He lived as a humble bachelor ascetic his entire life. The gold was merely a stepping stone to understanding the divine mechanics of the universe, not a means to buy earthly luxury.
It is such a striking image to end on. The devout mystic in his simple, soot-stained room, grinding volatile chemicals in a bowl of solid gold, trying to unlock the secrets of creation.
It really sums up the era.
It does. Okay, let's unpack this entire sweeping journey for you, the listener, because we have covered a staggering amount of ground today. We started with the literal dirt under our feet, the practical earthly need to navigate the sprawling deserts for the Hajj, and to map the oceans for the spice trade. That raw necessity forced geographers to fact-check the ancient Greeks and redraw the map of the world.
And that desire for cartographic precision demanded an entirely new mathematical language. It drove the systematization of Hindu-Arabic numerals. the revolutionary concept of zero, the invention of algebra, and the geometric solutions to cubic equations.
Armed with that new mathematics, they didn't just map the Earth, they built massive state-funded observatories to track the exact movements of the heavens. They accurately calculated the circumference of the Earth in the desert and theorized its rotation hundreds of years before the European Renaissance.
And staring up at those stars naturally led to decoding the physics of light. It led Ibn al-Haytham into a dark room with a pinhole to prove exactly how the human eye works, and it led Shirazi to unravel the geometry of the rainbow.
And finally, understanding the forces of light, gravity, and density led them into the laboratory, attempting to distill the very immortal essence of creation through the mystical science of chemistry and alchemy. It was a deeply, inextricably interconnected web of knowledge. Faith, administration, global trade, and sheer, unadulterated human curiosity fueled a millennium of relentless progress. It was a golden age in the truest, most dynamic sense of the word.
Truly.
But I want to leave you with a final thought to chew on. Throughout this entire deep dive, across every discipline we've covered, we've seen a recurring theme. We've seen how profound mysticism like the Sufi quest for spiritual perfection and hard empirical science like inventing the Olympic still, mapping the monsoons, and formulating abstract algebra were completely intertwined. Jabir ibn Hayyan was a devout mystic and a master experimental chemist. Al-Biruni was a theologian and an astrophysicist, calculating the conservation of momentum. They saw absolutely no contradiction between studying the creator and rigorously dissecting the mechanics of the creation.
In their worldview, one inherently fed and elevated the other. To study physics was to study the mind of God.
Exactly. But today, in our modern hyper-specialized world, we've built a massive, rigid wall between the spiritual and the scientific. We treat them as distinct opposites, often as outright enemies. If you are a serious scientist, you aren't supposed to talk about mysticism. If you are a mystic, you aren't supposed to care about empirical data. So the provocative question is this: what have we lost by building that wall?
It's a great question.
If the greatest, most explosive scientific golden age in human history was fueled by a holistic worldview, a worldview where the spiritual pursuit of perfection and the empirical measurement of reality constantly informed and inspired each other, could a return to that kind of holistic thinking be exactly what we need? Could tearing down that wall be the catalyst for the next great paradigm shift in human understanding? Something to think about the next time you use GPS to find a coffee shop, or type a 0 on your keyboard, or just look up at the stars on a clear night. Thank you for joining us on this deep dive. Until next time, keep questioning.